We find that the rain is naturally acidic because of the carbon dioxide that's there in our atmosphere. You see, as the rain passes through the atmosphere, the carbon dioxide enters into the raindrops, where it reacts with the water to form carbonic acid. Let's take a look. Here's a carbon dioxide molecule, here's a water molecule, some chemistry that may be going on inside a raindrop. The water and the carbon dioxide get together to form this material, which is carbonic acid. Let's look at it in equation form. Here's the equation. Carbon dioxide plus water gives rise to carbonic acid. And carbonic acid, as its name implies, is an acid. It turns out it's a weak acid. And because of the presence of this carbonic acid, rainwater has a pH of around 5, which is an acidic pH, right? I can show you the reaction between carbon dioxide and water right here in this bottle of seltzer water, which already has the CO2 and the water mixed together. Let's take a look at its pH, okay? I have our pH meter all set up. First I'll rinse off the electrode. Then I'll add the seltzer water. And you see the effervescence, which is carbon dioxide coming out of solution. And check this pH out. So something as simple as seltzer water has a pH of around 3.55. Why? Because of the carbonic acid that's within the seltzer water. Got another demonstration to show you. Here I'm going to take some water in a test tube and add to it a pH indicator. What's a pH indicator? It's a material that changes color for a given pH. This indicator I'm using is called phenolphthalein, and it has the property of turning to a pink color when the pH is above 7. When we look at this carefully, we see that it's colorless. That indicates to us that has a pH that's an acidic pH, a pH less than 7. I'm going to add a base to it. Watch what happens. And you see the pink color forming, which indicates we have a pH above 7. If I wanted to get rid of that pink color, what would I do? I'd add an acid. Okay? Where are we going to find an acid? Oh, how about carbonic acid? Why don't we take our breath and blow bubbles into it? So we add the acid, it becomes acidic again, and as indicated by the pH indicator. You're not saying I have acid breath, are you? Well, so do you. Very good. Because of the carbon dioxide that's in our breath. The carbon dioxide reacts with the water to form carbonic acid, you see. So we understand how it is that rainwater is naturally acidic. It's because of the carbonic acid it contains. What then is this idea of acid rain? Well, it turns out acid rain is really this. Rain having a pH less than 5, arising from reactions of airborne pollutants. You see, rainwater will naturally have a pH of 5, but when you have pollutants added to the atmosphere, the pH of the rain will drop down even further. And that's when we have what we classify as acid rain. Some of these pollutants include sulfur oxides. That would include sulfur dioxide and sulfur trioxide. We use the term SOx or SOx as a general term to indicate sulfur oxides. Nitrogen oxides are also a source of airborne pollutants that give rise to acid rain. That includes nitrogen monoxide and nitrogen dioxide, and they're just broadly known as the NOx. And so we have the SOx and the NOx that give rise to acid rain. But where do these atmospheric pollutants come from? There are a number of sources. One of them is from nature. We have volcanoes going off. And when the volcanoes go off, we have lots of gases spewed into the atmosphere, and that includes the sulfur oxides and the nitrogen oxides. And indeed, that will give rise to acidified rain. But interestingly enough, about 70% of the airborne sulfur oxides in our atmosphere come from human activities. And about 50% of the nitrogen oxides also come from human activities. You see, when you burn fossil fuels that have like sulfur in it, coal in particular, the sulfur reacts with the oxygen during the burning process to give rise to the sulfur oxides. When you have a car engine that's burning, we've talked about this before, the nitrogen and the oxygen combine to form, under the intense heat of the engine, they combine to form nitrogen oxides. And so here we have human sources of these airborne pollutants that can give rise to acid rain. Wait a second. How do we go from nitrogen and sulfur oxides to acid rain? Let's look at this. The conversion of SOx into sulfuric acid. Let's see, we'll take 2 molecules of sulfur dioxide and react it with oxygen. Where are you going to get oxygen? In the atmosphere. That's right. This is atmospheric chemistry. The sulfur dioxide and the oxygen in the atmosphere will combine to form sulfur trioxide. Sulfur trioxide will combine with water. Where are you going to get water? Again, in the atmosphere, say in the raindrop even. And they combine to form this material, which is sulfuric acid. Whereas carbonic acid is a relatively weak acid, sulfuric acid is quite a strong acid, you see. Let's look at the nitrogen oxides. 2 molecules of nitrogen monoxide plus 1 molecule of oxygen will give rise to 2 molecules of nitrogen dioxide. Got that balanced equation? Well, all you need to do is collect yourselves 3 of nitrogen dioxide molecules, react it with water, and you end up with 2 molecules of nitric acid plus another molecule of nitrogen monoxide, which can be recycled again through the first equation. But this nitric acid here that's formed is a strong acid, much like sulfuric acid. So we see, once you get these airborne pollutants, the sulfur oxides and the nitrogen oxides, through the atmospheric chemistry, you end up with sulfuric acid and nitric acid. And you dissolve the sulfuric acid and the nitric acid into the rain, and the pH drops. Now, that can be problematic when you have rain coming down with a low pH. It can be damaging to structures such as iron structures or even structures made out of calcium carbonate. For example, marble. Marble is a form of calcium carbonate. Many statues are made out of calcium carbonate. Chalk is made out of calcium carbonate. Let's look at what happens when we take some acid and add it to chalk. Here's a piece of chalk. It's calcium carbonate, and it turns out it's a building material for many of the structures we have. And if you were to add acid to it, watch what happens. Chemical reaction. We're getting carbon dioxide being produced here. And over time, we'll find that this chalk changes into new materials that dissolve. And if you have a statue made of this material, consider how it would behave in the acid rain. So you see how it is that the acidified rain can be damaging to structural features. So billions of dollars are actually lost each year because of the structural damage due to acid rain. So it has become a recognized problem. So what do? The solution? Try to cut back on the amount of sulfur dioxides and nitrogen oxides that we emit into our atmosphere. You could read a lot more about those efforts in lowering atmospheric pollutants in a later chapter in this book. Okay? It turns out that the amount of damage that will arise to, say, lakes is also dependent upon the local geology. Here's a lake which is maybe typical of a Midwestern region, Midwestern United States, where the lakes are lined with limestone. Limestone is indeed another form of calcium carbonate. And so the acid rain comes down and see the hydronium ions in the water droplets, and they accumulate within the water. But they don't really accumulate because there's calcium carbonate in there, and the hydronium ions will react with the calcium carbonate according to this equation here. The hydronium plus the calcium carbonate gives rise to carbon dioxide. This was that reaction we just looked at, where we saw the calcium carbonate, the chalk, reacting with the acid. Carbon dioxide came off as those bubbles. And so what's happening here is it's neutralizing the acid is what it's doing. So by having lakes with the calcium carbonate bed, we find that the acid rain may come down, but it just gets neutralized. This is in contrast to other geological regions where the lakes are lined with granite rock. Now the granite is more inert. So what happens is the acid rain comes into the lake and the hydronium ion concentration simply builds up. And the pH can get lower and lower. The more hydronium ions you've got, the lower the pH. It can get to the point where it can be damaging to the aquatic life living in the earth. What do you do? Suggestion? Well, we could take lime, chalk, calcium carbonate, and just spread it through all these lakes that are so-called acidified lakes. And that would raise the pH. And you know what? That works. There's an economical problem there, though. There are a lot of lakes that would need to be treated. And the tons of calcium carbonate you would need to transport to these lakes. It's beyond reason. Better to just cut the source of the acid rain. And that's how it is. We focus on cleaning our emissions. So whereas the rain is acidic, we find our oceans are alkaline. Alkaline means that it has a pH of above 7. This, we find, has an effect on the levels of atmospheric carbon dioxide. Let's take a careful look. Let's start off by looking at a freshwater lake. The pH is acidic, it's less than 7. And we find that the carbon dioxide will go into the lake. It will react with the water to form carbonic acid, as we've seen. But then you know what? The carbonic acid can transform right back into the water in the carbon dioxide. It's a very dynamic situation. And the carbon dioxide comes back out. So the CO2 goes in, forms carbonic acid, goes backwards, and then the CO2 comes back out, which is in contrast to what happens in the oceans. Over here in the oceans, where the pH is around 8.2, and the reason the pH is about 8.2 is because of the dissolved solids that are in the ocean. The CO2 goes into the ocean and it forms carbonic acid, right? There's our old friend equation right here, forming carbonic acid. But then, what happens to the carbonic acid? Well, it reacts with the basic materials that are within the ocean to form these salts. And the salts will accumulate to the point where they become insoluble and they'll precipitate to the bottom of the ocean. What happens is the carbon dioxide goes into the ocean, forms carbonic acid. The carbonic acid is neutralized, forms salts. Salts go to the bottom of the ocean, and no CO2 comes out, or not much CO2. It's a very dynamic equilibrium. The net effect is that there is an input of carbon dioxide into the ocean. So the ocean becomes a genuine carbon dioxide sink. We pump more carbon dioxide into the atmosphere, it means we're pumping more into our oceans, you see. Now, it's true that the oceans have a moderating effect on the levels of atmospheric carbon dioxide, but even they have a limit. We find that the levels of carbon dioxide have in fact been increasing over our recent history. This is data from the Mauna Loa Weather Observatory, taken from Hawaii, where they've been measuring the atmospheric concentrations of carbon dioxide since 1957. Here we see at that time the levels were about 310 parts per million. What's that mean? For every million molecules, 310 of them are carbon dioxide molecules. And that was the level back in 1957, and it has been rising steadily. The year 2000, it's upwards around 370. It's about a 20% increase in the amount of carbon dioxide in our atmosphere. So what? Why not have more carbon dioxide in our atmosphere? Plants love carbon dioxide. Won't the plants just be growing faster or something like that? Well, it turns out we understand that carbon dioxide is known as a greenhouse gas. What's that mean? It means that it traps the heat within our planet. And the more greenhouse gas we have, the warmer our planet can become. It's important that we have carbon dioxide, some carbon dioxide there to trap the heat. Otherwise, our planet would be a lot colder than it is presently. But if we have too much carbon dioxide, that can lead to drastic changes in weather patterns. And you can read more about that in the later chapter in this book on atmospheric chemistry. Good chemistry to you. When we talk about acids and bases, we're talking about a behavior of molecules. If it's an acid, it tends to donate hydrogen ions. If it's a base, it tends to accept hydrogen ions. Now, it's a behavior, you see. And you know how people have different behaviors, these molecules have different behaviors. Some, turns out, can behave as a strong acid. Others can behave as a weak acid, others strong bases or weak bases. You see, some like to donate the hydrogen ions forcefully. We call them strong acids. For example, say this is a hydrogen ion, also known as a proton. And let's say I'm a strong